All right, Mr. G Math coming at you live, 7202. This is Wednesday, September 6th. Today's lesson is on concavity. I'm going to remind you that all your side conversations get picked up, so there'll be nothing personal. Everyone will know what you're sharing with whoever. Today's lesson is on concavity and the second derivative test. So last lesson was on increasing and decreasing and the first derivative test. This lesson is on concavity and what that means and the second derivative test. So let's read together. Some of this we did in summer school to understand concavity when we're talking about does it smile or frown. So a graph with this shape is called concave upward. The tangent lines lie below the graph. The slopes of the tangent lines are increasing, which means the second derivative is positive. So I want you first to get the sense of the shape. The shape, when you look at it, is smiling. Do you see that? A smile means concave up. But now the second concept, do you notice that the slopes are increasing left to right everywhere? So if I look at the left, the slopes are negative. Then it gets to a point where the slope is 0, and then the slopes become positive. So all the way, far left to right, everywhere you look, the slope on the left is smaller than the slope on the right. Or the slope on the right is always bigger. Because a negative number is smaller than 0, and 0 is smaller than positive numbers. And as you get steep to the left, if it was like negative 4 is smaller than negative 2, which is smaller than 0, and so on. So technically, when you look at the slopes, when the slopes are increasing, it means it is concave up. So when you look at the top picture, the slopes are what? Increasing. They don't change. In fact, if it changes from increasing to decreasing, we call that a point of inflection, and the concavity has changed from a happy face to a frown or vice versa. So if it's concave up everywhere, that means from left to right, the slopes are increasing. Okay? Okay. How about the other way, concave down? Instead of smiling, you are frowning. Now when you look at the slopes, what are happening? They're decreasing. So if you just look at a simple case here, on the left we have a positive slope. Then we went to 0, and then it went to a negative slope. So if you just think of it in that little jar, right, that you go from positive to 0 to negative, what's happening to the slopes? They are decreasing, right? They're getting smaller. When it's decreasing, what does it create? Is a frown, right? That concavity is down rather than concave up. So informally, you look, does it smile or frown, right? Smile is concave up, a frown is concave down. Formally, when you look at the derivatives, the slopes, if the slopes are increasing, it's concave up. If the slopes are decreasing, it's concave down. Okay, that's more formal, right? Looking at the slopes. And when happens the point where it's neither? It's not smiling or frowning. It changes at that point. That's called the point of inflection, where the concavity changes. All right, so you can see a little box that says concave up. The slopes are becoming positive, right? They're increasing, and it looks like a smiley face. Concave down. When you take the second derivative, it would be negative, and it would give you a frowny face. So a point on a graph is called the point of inflection if the graph has a tangent line at that point and the graph changes concavity at that point. So it still has to be continuous, right, at that point and have a tangent line and that. If it doesn't have a tangent line, what would that mean? It could be a sharp turn or a corner, right? Any of those things wouldn't apply then. So in other words, it has to exist for the first derivative and the second derivative. If it's undefined for the first derivative, automatically there can't be a point of inflection doing the second derivative. Okay, okay? Okay. Okay, let's look at the examples. Number 1. It says, use the graph at the right to answer these questions. Base your answers on the appearance of the graph. On which intervals is the graph concave up? So look at it. and see where is it smiling at you. And I'll write it down if you're right. Can you tell me one interval where it's concave up? What is it? -2 to 0 is wrong. -2 to -1 is right. So what happens after -1? It's no longer smiling, but it's frowning. So where's it concave down then? From -1 to... So from -1 to +1, it frowns. Do you see that? So from -2 to -1 is half a smile. Then a full frown. And then what happens from +1 to 2? All the way to what number? So from 1 to 3, it smiles, right? All the way. And then what happens? Oh, I didn't mean to do that. Put it in the wrong spot there. So from 1 to 3 is concave up. What happens from 4 to 5? Well, at 4, there's a sharp turn, right? So from 4 to 5, it's still concave. No. It's half a smile, right? But why did I separate it? Why didn't I just go from 1 to 5 is concave up? Because the derivative doesn't exist there, right? At 4. So at that point, at that 4, we have to separate them. So from 1 to 4 is a smile, right? From 4 to 5 is half a smile. But exactly at 4, it's neither, right? It's not part of that. So I had to separate from 1 to 3 and 4 to 5. 1 to 3 is an easy smile to see, right? From 4 to 5 is half a smile, a little more challenging, but can you see that? And then from 5 to 6 is half a frown. So you can see the concavity, right, by looking at the curves. On which intervals does the graph have no concavity? So from 3 to... Now, why is there no concavity from 3 to 4? And it's just a slanted line, right? There's no curve there. There's no smile there, right? And if you take the second derivative of a slanted line, do you know what number that would be? Any slanted line, right? You take the derivative, that's the slope, but then you take the derivative of that slope of the line, it's always going to be what? 0. 0 is not concave up or concave down. It either has to be positive or negative. But the second derivative for a line is 0, so there's no concavity for a line. All right. Where else is there no concavity? It's hard to see because it's right along here. Because it feels like it's like on top. I know, it's like camouflage. Fun word for today. So do you see from 6 to 7? It's camouflage, but from 6 to 7 is a horizontal segment there. Why is there no concavity for a horizontal segment? Again, the second derivative would be equal to... So you still have a second derivative, but it's 0. Because the derivative of a horizontal line is 0, and the derivative of 0 is 0, but it's not positive and it's not negative, so it's not concave up or concave down. So there's no concavity in that interval. Where is there a point of inflection? A point means I need an x and a y coordinate. So at -1, 1 is a point of inflection. Is there any other point of inflection?
5 and 1.
So I'm going to take this back. So why is -1, +1 not a point of inflection? Because you cannot take the derivative at that point. Do you see that corner there? The derivative to the left is not the same as the derivative coming from the right. But how about this one right here? +1, +1. Can you see that's a point of inflection? So go back. Why is -1, +1 not a point of inflection? Because you can't take the derivative there. Can you see the cusp, the corner there? But you can do that here. So at +1, 1, there's a point of inflection. Where's the other one? Is this going to be a point of inflection up here? No. This point here is still in the concavity up, right? No. Why no? Because you can't take the derivative. Is this a point of inflection? Good. That's at 5 and 1. And again, is this down here a point of inflection? Because you can't take the derivatives. If you can't take the derivative at that point, then you can't have a point of inflection. So analytically, we find concavity intervals and points of inflection by using a second derivative number line, just like we did for first derivative, right? But it's going to be second derivative. And then the procedure is to parallel the same one we just did in the last lesson for increasing and decreasing and relative extrema by using a first derivative number line. So let's practice this. Turn the page. Let's read it together. Number 5 says, determine the points of inflection. Does that mean I need an x and y coordinate? What's the word? Point. Thank you. And then it says, discuss the concavity, which means where's it concave up, where's it concave down, or where is there no concavity? That's what it means. Okay? So what do I need to do first? Yay! Let's do that. X to the fourth will become 4x cubed. X cubed. 3x squared. Negative 3x squared. Negative 6x. God bless you. Are we done? No. Second derivative. That would be 12x squared plus 6x minus 6. Now what are we going to do is we're going to make it equal to 0. If there was a place where the second derivative is undefined, it's the second one, not the first one, we'd also look at that number. But there's nothing that makes this undefined. What would be a great first step to do here? Divide everything by 6. I'm going to do that. That would be 2x squared plus 1x minus 1 equals 0. So how did I reduce it down? Divided everything by 6. How are you going to solve that? By factoring. That's right. Go for it. Can you factor that, please? You can draw a diamond and box, but I'd be disappointed in you. Both 2 and 1 are, I know, sorry about that. Both 2 and 1 are prime numbers. What does that mean? There's not a lot of options. Like, how do you get 2x squared? You have to go 2x times x, right? There's no other options. There are no other integers that would make 2x squared. 2x times x. What's the other number I care about? 1. What's the only way you can make 1? 1 times 1. What's the only thing you have to think about? Which one's positive and which one is negative? Can you do like a little foily stuff in your head to see where the negative should go and where the positive should go? Because they have to combine to positive 1x. Which one's negative and which one's positive? You do your little rainbows, right? Which one, when you combine like terms, gives you positive 1x? So the first one must be negative and the second one must be positive. Why? Negative 1 times x is negative x. 2x times 1 is positive 2x. Together that makes positive 1x. When they're prime numbers, I'm looking at the first number and the last number. That should be easy to guess and check quickly, right? It's when they're not prime that you need other techniques. All right, solve for x in your head. The first factor gives you what answer when you make it equal to 0? Add 1 and divide by 2. The second one? That's it. What did we just find were the critical numbers for the second derivative test? If there was any numbers that made that undefined, then you would do that. But it's a polynomial. There's nothing that makes it undefined. Can you put a number line in? What goes first? Negative 1. What goes second? 1/2. Can you test for concavity? Where do I go to test? To see? Yeah. So you can do either one here, but I'm going to circle it right here so you see it again. What happens when you plug in negative 1 million? Or negative 1 billion? Good. Because it's going to square, which is positive. It'll be way bigger than the middle term, right? Way bigger. So negative 1 billion gives you that answer that's positive. What's the nicest number to plug in between negative 1.5? What does that give you? Something positive or negative? Negative. Beautiful. And then when it's greater than 1/2, 1 billion again. Positive. So what did we just find? So can you tell me where it's concave up? What intervals? From negative infinity to negative 1 and from 1/2 to... infinity. Where is it concave down? Do we have any point of inflections? Do you see where the concavity changes? If the concavity doesn't change, it's not a point of inflection. Did it change from positive to negative here? So we have a point of inflection when x equals what? -1. How about, is there another one where it changes? At what other x value? So, point of inflection at -1, and there's another one at 1/2. Oh, this is going to go away from me. All right, so what do I still need to find? The y coordinate. See if I can find a pen that works. I think I'm good. There we go. The backup is in. So, where would you plug in -1? I'm going to save you pain and just tell you the answer is -2. Where are you going to plug in 1/2? Again, I'm going to save you some pain, and the answer is 7/16. Yes, you need to know some basic arithmetic and algebra, but I really want this lesson to focus on the calculus and not the headache that to get 7/16 is going to create right now. So be patient with yourself with the arithmetic, but I don't want a headache over that right now. Calculus. So, can we recap what we did again? We did the first derivative, and then we did the second derivative equal to 0, solved it. We also saw, is there any x values into the second derivative that makes it undefined? No. So what are the critical numbers for x? -1 and 1/2. We tested the signs with the second derivative. There was a sign change at -1, a sign change at +1/2, and then we use those to find the y-coordinate, to find the point of inflection. From the number line, you can see intervals of increasing and decreasing. All right, number 6. It's fine. It's 10 after. I got 7. And if I need to continue just for a quick minute after or whatever, I might even hold you for the break for a moment. I know. Cruel. So, 6. You're given a function. Do you have to take the second derivative? The answer is no. Why? Because it already gives it to you. So it says, list where that is concave up or down. So what do I do to find that? I draw a for the second derivative. Whenever you have a fraction, I'm going to tell you again and again and again, what makes the top 0? What makes the bottom 0? Okay? So look at the top. What number would you plug in that would make the top 0? So you're going to say, wait a second, no matter what number I plug in, the top will always be positive. There's no number to plug in to make the top 0. Correct? If you try to make that equal to 0 and solve, it would only be an imaginary answer for that. There's no real numbers for the top. Take a moment, breathe through it, realize it. Yes? The bottom, there are 2 numbers. What are the 2 numbers that make it? Close. 2, right? Yeah. You meant 2. So a -2 and +2. So again, why are those critical numbers? That's where right is right, where the second derivative is undefined. Well, just because the second derivative is undefined, we have to go back to the beginning. Look at the beginning and look at the bottom. Does it make the beginning undefined as well? So yes, what we just came up are vertical asymptotes. That's going to be important to have a better understanding of concavity. I'm going to plug in a number smaller than -2. So if you plug in a number like -100 or -1 billion, I want you to notice the top number is always positive. And the bottom, when you square a huge negative number, it's going to be positive, right? Subtract 4. So positive over positive is positive. Plug in the best number between -2 and 2, which is 0. The top is always positive. The bottom will now become negative. So a positive divided by a negative is negative. Now plug in positive 1 billion, and again, greater than 2 is positive. Where is this concave up? From -infinity to -2. Where else? From 2 to infinity. Where is this concave down? To 2. Point of inflections. at what x values, and now we'll figure out what the y. Is there any concave change? Is there any concavity changes? Where? At -2 and 2, right? Wow, I'm just going to write down none then. Why? Because there's no points on the asymptotes, right? Get that? Get that? So there is no points of inflection. Yay! Let's keep reading here. Maybe you'll get a break after all. The second derivative test for relative extrema. What does that mean, relative extrema? That could be both relative maximum and relative minimum. We already know a method to do that, right? That's the first derivative test, and see where it's changing from increasing to decreasing. It says use the first derivative to find critical numbers, but you plug the critical numbers into the second derivative and analyze the concavity. So if it's concave up, what did it create? A local min or max. Let's try it again. So you're still going to find the critical numbers from the first derivative, right? But if you plug it into the second derivative, right? If it's concave up, it creates what? A minimum. But here's what's confusing. You ready? Concave up means when you plug it into the second derivative, the answer is actually going to be positive. If you have a positive concavity, what you just found was a minimum. Look at it. A positive concavity means you found what? A minimum. A negative concavity means you found a maximum. And that's a little confusing at first until you practice, right? So look at this. Use the second derivative test to find where the relative min and max are. Let's do it. First, take the first derivative. What's the first derivative here? 4 times -3 is -12x cubed. 2 times 6 is 12x. Make it equal to 0 and solve it. What's an obvious thing to divide out? 12, sure. And then keep going. I'm going to divide out -12. So it becomes positive x cubed minus 1x is equal to 0. What do I do next? Factor. What do they have in common? What are the two answers for x?
Why did you take out an x squared?
Why did I take out an x squared? I just meant to take out an x. Crazy. Take out an x, and you get x squared minus 1. X squared minus 1 is the difference of squares. Let's make sure we're right. There are 3 critical numbers. 0, positive 1, and negative 1. We're not going to do a first derivative number line. Instead, we're going to take the second derivative. What's the second derivative? Look back. This part right here. Not the reduced one. Negative 36x squared plus 12. Do not make it equal to 0 or nothing. What we're going to do is this. We're going to plug these numbers into the second derivative. So take the second derivative. What are we going to plug in? I don't care what the number is. I care if it's positive or negative or neither. If it's neither, then it's right. All right. There's no concavities, can't be relative maximum. So plug in 0. Is the answer positive or negative? What does that mean? Which means relative minimum at x equals 0. If I plug in positive 1 into the second derivative, is the answer positive or negative? A negative concavity means I found a relative what? Again, the second derivative, plug in negative 1 into the second derivative. Same answer, right? Again, it's negative. What did we just find? Again, right? So if the concavity is positive, you found a relative minimum. If the concavity is negative, you found a relative maximum. So you'd plug in 0 back to the way beginning, and you'd realize that at 0, 0 is a relative minimum. You would plug in positive 1, and you'd realize that positive 1 and positive 3, and you plug in negative 1 and get the same answer, that we have 1 relative minimum and 2 relative maximums. That's called the second derivative test, where you plug it into the second derivative and look at the concavity. Concave up means you found a minimum. Concave down means you found a maximum. Is there anything fun on this side? Just give it 1 second here. Got one question, and I'll let you run. 8. And then it's on video. So even if you don't listen to me, you can at least look back at the video. Then I'll let you get a break. I'll even let you come back late a little bit. Maybe. So g at x is a function, and it gives you information. The first derivative at negative 3 is equal to 0, which means negative 3 is a what? A critical number, correct? At negative 1, it's equal to 0. What does that tell you? At negative 1 is a critical number. At 0, it equals 0. What does that tell you? At x equals 0 is a critical number. And at 2 is equal to 0. So what does that tell you? So what are all the critical numbers for g? So the critical numbers, I'll call it Cn, are when x equals negative 3, negative 1, 0, and 2. Then it says the second derivative of each one, right? And it says find the x values where you have a maximum or minimum. This is going to be super quick. So at negative 3, when you plug in, is the second derivative positive or negative? Do a little parabola. It will help you. What did we just find if it's positive? Minimum. At negative 1, is the answer positive or negative? So what did we find? A maximum. Do little parabolas. At 0, what is it? Neither. Right? There's no concavity there. It doesn't create a max or a min. 2. Well, they give you 1. Do we need 1? No, because it's not a critical number. Don't fool me. Positive 2? Positive or negative? So what did that create? So we have a relative maximum at what x values? When x equals negative 2, and that's it, right? Just this one right here? Where's the relative minimums? They didn't say find the full points, just at the x values. Where do we have a minimum? When x equals? Huh? Oh, wait a second. That's the y value. So what's the x value there? That was a negative 1. It just looked like a 2. So the relative minimum, what's the x value? Let's do this one right. When x equals negative 3, where else is there a minimum? When x equals 2. All right. So what did we learn today? We learned about concavity. What concave up smiles, concave down does not. It frowns. And the second derivative test means when you plug into the second derivative, if something's concave up, we just found a minimum. If it's concave down, we found a maximum. No? Concave up, you found a minimum. Concave down, you found a... Oh, over and out. Go